All right, so let me start by introducing Naila Murray. I'm very pleased to have her, especially because Naila and I were working on iClear 2021 for several months, starting from last fall all the way to spring of this year when we actually had the conference. So it's very nice to have you here. And Naila was at Princeton for her undergraduate, and then she was in Barcelona for her PhD. And then she worked for a long time at Xerox Research Center in Europe, doing research in computer vision, including topics like fine-grained visual categorization, image retrieval, and visual attention. And then she was leading the computer vision team at Xerox Research Center, and then it became Naver Labs Europe. And last year, I believe, last year, she joined Facebook AI Research as a research engineering manager. And she's done a lot of work for computer vision and machine learning conferences, including iClear 2021, when we were both co-chairs, co-program chairs. And other than that, also CVPR and ECCV. And Naila's current research interests include continual learning and multimodal search. And today she's going to talk to us about unsupervised meta-domain adaptation. So please begin.
All right, thank you so much, Alice. Thanks for this invitation. It's nice to be able to interact again in a different format than earlier this year. And thanks everyone for joining this talk. It's a pleasure to be here. So why don't I start by sharing my screen? All right, so hopefully everyone can see this. Let me just pull up my pen as well, or actually, yeah, that should work. Okay, so, oh, actually, let me just hide this as well on the side here. All right, so thanks everyone again. As Alice mentioned, so I'm going to discuss with you today some recent work from some colleagues and myself on unsupervised meta-domain adaptation. And this may be a concept you haven't been introduced to yet, so don't worry, we'll get to that. And also we'll be discussing applications to fashion retrieval in particular. So this is joint work with colleagues Vivek Sharma, Diane Larlus, Mohamed Saki Safras, Rainer Stiefelhagen, and Gabriela Chirka. So just to start off on the motivation for this work. So this work is very motivated by the need in many applications, especially many real world applications that use machine learning models in terms of dealing with data distribution shifts, right? So stepping back a little bit, let's think of a standard machine learning pipeline, right? Which looks kind of, in a very cartoon way like this. So you have some set of training data, usually or very often with annotations as well, if you're in a supervised setting. Then using this data and some sort of objective function, you're going to optimize some objective function with respect to their parameters and some task you want to achieve. And this is going to give you a trained model. And then you're going to deploy this, right? So the idea is that you would deploy this, at some sort of testing time or real world time to give you some sort of predictions, right? Some set of predictions on a test set of data. So what's crucial in this typical pipeline is making the assumption that the training and the test sets have been generated by the same data distribution. However, as you could imagine, right, in many real world applications, the data is constantly shifting, right? So if you take a look at my little toy data set here, this is a data set which has a certain distribution of different items, or let's say semantic categories. And this can shift with time, right? So let's imagine you're in an online shopping scenario. And you can imagine that from year to year, the items within an online shopping catalog that you might want to categorize would certainly change, right? It might change in terms of the actual items that are within that catalog, and then just the appearance of different items, right? So you might have a set of, for example, shirts, t-shirts or shoes And you'll probably always have shoes, but they will look different, right? They'll have different appearances, there'll be slightly different styles, etc. And then as time goes on, this shift will continue. So if you have models that are trained to predict certain aspects of these data sets, these data distributions, if they're trained on older distributions, and they're not going to give you accurate predictions as time goes on and as the data shifts. So there's a large body of work around techniques called domain adaptation techniques. So this is a set of techniques for addressing exactly this problem, right? Distribution shift. And these distribution shifts can be in a variety of ways, as I was kind of mentioning before. So they can, for example, be semantic. So if you look at this tour example here, you'll see that the semantic meaning of some of these items will change. So for example, as time goes on, you may have dresses and they may no longer appear, whereas new items, for example, footwear might appear. So these are kind of semantic changes. They could also be appearance-based, right? So in these cases, for example, you have the same distribution of semantics, but the appearance of these have changed, right? So for example, the pants are a slightly different color. So in domain adaptation, there's this concept of source and target domains, right? And the idea is to adapt from some source domain to some target domain. Okay, and you will see these concepts show up again throughout this talk. So, and another important distinction, whether these techniques are supervised or unsupervised. And so what that means is, in a supervised case, if you're trying to adapt a model based on this source domain to some target domain, you would have some supervision that allows you to make the transition or to train your model to adapt to this new data set. And you may have cases if you do not have such annotations, which will be actually the case of our approach that we discussed today. So to give you a bit more background into unsupervised domain adaptation, there have been, there's quite a large body of work on various methods, right? Starting from certainly many non-deep learning based methods. So what we will call shallow methods, which include things like relating different data, metric learning approaches, also learning different subspace representations, or matching distributions across domains. More recently, there've been, as you might imagine, there've been quite a few deep learning-based approaches, which have used things like discrepancy minimization, adversarial losses, or even generative modeling to tackle this problem. Another important thing to notice is that many of these works focus on image categorization, or classification, or even just generically, right? Even if you don't think about computer vision, but in other domains, there's a strong focus on categorization, and you'll see that in this case, we're motivated by a different task. So I'll deep dive into just one kind of representative approach because it kind of gives a sense of how domain adaptation is actually achieved in many of these in these applications, and also because it's quite relevant to what the method I'll be describing a bit later on. So in this specific case of discrepancy minimization, which is a very very popular approach, if we set it up here, we have these two domains, right? A source domain and a target domain, DS and DT, which are characterized by two distributions, A and B respectively. We also have some embedding function phi, parameterized by theta, that transforms an image into some vectorial representation. Okay, so given all of this, what we'd like to do, what discrepancy minimization does, is it aims to minimize the function you see here. And what this is a simple distance between the expected embeddings of images, or it doesn't have to be images. In this case, we're dealing with images, but it could be sort of any signal, between the expectation of the embeddings across these two domains, right? So you would calculate this ideally by computing the expected embedding across the space of distributions of images in the source domain and in the target domain, and then you'd like to just minimize that discrepancy. So why would this help with domain adaptation? So the the intuition, the kind of hypothesis here is that if you have these two distributions, which are related in some form. So for example, if we think of the case where we had the two shopping catalogs and they differed only in terms of their appearance. So for example, some of the items might have changed the color. What you would like to do is to learn representations, right? So learn this function phi that is invariant to this specific feature, right? So you could imagine that in the absence of this minimization technique, you might have a phi function that's very reliant on color to make predictions. And given that you know that color is not an invariant not an invariant feature across source and target domains, you would like to kind of reduce the reliance on that signal by learning a function that will perhaps pick up different signals that are more that are domain invariant. So this is the hypothesis of this technique, and it has worked very well in practice. So here, and I'm referring to this work by Long et al. In this work, the authors proposed to use an architecture, a deep learning architecture that looks like this. And it's interesting because it has certain parts that are learned and certain parts that are not, right? So in this case, what the authors have done is they have a sort of what you might call a deep backbone, right? Some architectural backbone that you can see here. I don't know, hopefully you can see my pointer. Alice, thumbs up if you can see my pointer. Awesome, thanks. Great. So there's some part that you can call this like some sort of embedding function phi, right? So at least some pre-embedding function phi, maybe not phi, but an input to phi. And then there's some portion that's learned, right? So this would be what you might call the supervised portion, okay? And this is learning an embedding function. At the end of this would be a phi here, okay? That's giving you some representation. And at the same time, you're learning jointly, in this case, to reduce this discrepancy, right? So whatever loss function is used to learn these embeddings, it's also, there's another component of this loss function that also includes this objective, this minimization of this function as well, right? And what this is doing is it's saying that we want to also compute this embedding here for the target. And what we want is that the distribution between these two, right, the embeddings from the source and the embeddings from the target, to be minimal. And so, yes, and so you will see kind of echoes of this throughout the talk. So that's a brief introduction to domain adaptation, unsupervised domain adaptation. So now I'll introduce you to the specific application we're interested in. So this is the application of cross-domain image retrieval. So here, just to set up the problem, and specifically we're looking at images, but a lot of these things are quite applicable to other modalities. So in this case, you're given some image, let's say like an image from a consumer, and this user would like to take this image that they've perhaps created. Let's say, for example, they've taken an image of a dress like you see here, and they would like to be able to find this dress online, ideally in some store because perhaps they want to purchase it, right? So they will take an image perhaps with their smartphone, most likely, and they will search through this database of images from online catalogs. Right? And what they'd like to do is to retrieve an image that is of the same dress, or at least maybe a similar one, perhaps a highly similar one, from what you can consider to be a pretty vast collection of potential items to search from. Okay, and so this is called cross-domain image retrieval because there is a domain gap between consumer images, so these images that somebody might take on their cell phone, and a shop image from a catalog. And the difference in the domains here would be things like the qualities of the different sensors. So in one case, you have a smartphone camera. In another case, you typically have a more professional camera that somebody might take to take these catalog photos. The style and the composition would likely be different as well. So there are these sorts of differences that result in this cross-domain problem, right? So note here that this is a different domain gap than the one I've mentioned before between source and targets, but it's just another type of gap that you can have between data distributions. So for this problem, this has certainly been tackled a fair bit in the literature, and what's typically done is we learn some embedding specify that is domain invariant, right? So it's very similar to the case I was mentioning before. What we'd like to do is to learn using some objective function an embedding that allows specifically to have an embedding space where items that are relevant to each other, so for example, these two dresses, are close in that space, and items that are not relevant, right? For example, this pretty different clothing item are far away in this space. And what this allows you to do is once you have this relevance feature be represented in the embedding space, then you can perform retrieval by simply looking for nearest neighbors in that embedding space, right? So you can imagine, that at deployment time, you have this query image and you want to search through the space of catalogs. What you're going to do is you're going to represent every catalog image with an embedding. You're going to compare your query embedding to the database embeddings, and you're simply going to do, for example, a dot product and then return the most similar ones, right? So this is what we like to do. And so this is what we call a consumer to shop retrieval scenario. And this is the application we'll be looking at. So let me try to remove this. Oops. Sorry, just give me 1 second.
There's a chat message that says this seems to be a Zoom annotation. So you may have to do something.
Oh, I see. Because yeah, I was trying to figure out if it was me, but I don't think so. Okay. Well, if someone, oh, awesome. Perfect. Perfect. Thank you so much. Great. So where were we? We were discussing cross-domain image retrieval. And as you saw in the previous slide, it's very critical that we have these, what we call triplets, right? So let me go back. So you see these 3 images. We have one query image, we have some relevant image, which we call P for positive, and then we have a negative image. And so we will use this as training data to train these embedding functions. Fine. So what happens if we don't have access to these triplets, right? Let's imagine you're at training time, you're going to need an image of a consumer item, images of both a relevant and a non-relevant image from this shopping catalog, right? And this may not be available in there are many applications in which you would not actually have that. So for example, this happens pretty naturally in practice, like when, for example, a new shopping catalog is introduced, right? So let's say that, there's this new fall collection and you'd like to be able to retrieve based on that, but you don't have any images, you don't have any relevance labels between consumers who've been looking for this in the past and who've already submitted their queries and this new catalog, right? Because it's new. So you're not going to be able to collect this type of data, at least at the beginning, right? So this is some kind of cold start problem. And even so, right, you could tell yourself, well, okay, we have this new catalog coming on, so we can simply just collect the data. But certainly you don't really want to be doing that every time new items come online, right? You'd like to be able to have something which would adapt to new data. And of course, it's for the reasons that I just put here, right? That they're laborious and expensive. And then also, yes, I mentioned here also there are privacy concerns as well every time we collect consumer data. So as much as we can avoid that, the better. So we're going to tackle this more challenging and realistic scenario by adapting a cross-domain retrieval model that was trained on some source data set to a target consumer to shop data set. And for this, we're going to use what we call meta-domain adaptation. So here's the outline for the rest of the talk. So I'm going to introduce this concept, like what do I really mean by meta-domain adaptation? Then I'll describe the specific approach that we have, that we've proposed for this. And then I'll just go through some experimental results at the end. So once again, right, looking at our scenario, we have these this data set, right? So we have a set of shop images, we have a set of consumer images, and this constitutes a source data set, okay, with these two domains. So we have the domain of shop images from the source, and we have a data set, well, a set of images of consumer images from source as well. And then let's say we have, so I'm going too fast. So as I mentioned before, there is this domain gap between these two domains, right? And as I mentioned, like this domain, this gap would represent things like the types of cameras that were taken, the style, etc. Now, let's imagine we have another set of data, right? So this could be what we're calling our target data and our target domain, which once again also has shop images and may or may not have consumer images. And as I mentioned before, very often in many practical scenarios, we will not have consumer images. And in fact, we'll be assuming we don't have those, right, in this specific case. And so this constitutes some target data set. Okay, so let's imagine this is like sort of constitutes our new application space, and we would like to adapt the model that was trained here to this new case. So, right, so this has a domain gap as well. And then what we call a meta domain is, for example, all the images of shops, right? So this is kind of a meta domain because it's a domain that really goes across different data set distributions. And similarly, we also have a consumer meta domain. And as well, you would see that there is some consumer meta domain gap. And so this meta domain gap, it's very similar to domain gaps that you would find across these, right? We would expect that generally speaking, shop images are perhaps higher quality, a bit more professional looking than consumer meta domains. And we expect this gap to be consistent across specific data sets. So just to reiterate this, so we define a meta domain as a high-level grouping of similar sensor domains. So for example, shop images from different sources all belong to a shop meta domain. And similarly, the consumer meta domain consists of available consumer images from different data sources. So, okay, so we've kind of built up the scenario. And so as I mentioned before, we're going to approximate this domain gap, okay, between our target data set by a meta domain gap, right? And I think this is a pretty reasonable one because what we would expect is that even if we've never seen these consumer images before, we expect the kinds of that at least some of the difference, right? Some of the gap between these two is likely to be sort of generic across specific data sets, right? So we're assuming that we can, to some extent, approximate this gap by this meta domain gap. Right, so okay, this is sort of just reiterating once again, right, that we're assuming that this meta domain gap is a generic gap between all possible shop images and all possible consumer images for a given product. So yes, and then it corresponds in our case to, for example, photographic style. Okay, so that's hopefully a clear meta domain adaptation, what that means. So now I'm going to discuss how we're actually going to do this, right? What our proposal is for this. So what we aim to do is to do a model adaptation technique, right? That's going to adapt some existing consumer to shop retrieval model to a new target data set. And as I mentioned, it's one that has no consumer images. So we're going to take a learning to rank approach, and I'll discuss in a bit more detail in a slide or two. Right, so this is a very standard approach for consumer to shop retrieval tasks and for quite a few instance level retrieval tasks generally. And it usually requires relevance labels between shop and consumer images, right? So if you think back to the slide I presented a bit earlier on that showed these triplets, to construct these triplets of query image, relevant image, and non-relevant image, you need to know what's relevant and what's not relevant, right? So these relevance labels are required for this approach. As we mentioned, we're interested in a scenario where consumer images are unavailable, which means that these consumer image pairs are unavailable as well, right? Which makes constructing this triplet not possible. So what we propose to do is to mine pseudo labels, to try to mine for relevance labels using a clustering approach. Then we're going to use these pseudo labels to learn this meta domain invariant embedding using our standard learning to rank approach. And then simply, as I mentioned before, now that we have this embedding space that conforms to our notions of similarity, we can simply use a deployment time, a dot product, for example, to rank images by relevance. Okay, so let's dive into this. So first, learning to rank, right? So once again, we have our standard phi function, right? That's parameterized by theta, and that transforms an image into some vectorial representation. And to learn theta, we're going to use the triplet ranking loss, a very standard learning to rank loss. And so this is formulated here, where we have Q as a query image, P as a positive or relevant image, and then N as a non-relevant image, okay, for that query. So what this is saying basically is that you have these are distance functions, right? D is a distance function between these two embeddings. And it's simply saying that if I compute the distance between my query and my relevant image, and I compute the distance between my query and my non-relevant image, I want this distance to be smaller than the distance between the query and the non-relevant image by some margin M, okay? So it was a very intuitive notion, basically saying that we want to train a parameter, we want to train a function parameterized by theta, which enforces this, this geometry. And so to do this, we need these triplets, right? These QPN triplets, right? And we use triplets. There, you can think of all the different combinations, like this kind of combinatorial list of potential triplets that you can do between consumer images and source images, right? So we can have these intra-domain triplets where we're comparing only triplets within consumer images or triplets between shop images. But crucially, we do need these triplets, right? We need these triplets between consumer images and shop images, because these are the triplets that are going to enforce this domain invariance. So as I mentioned, right, we don't necessarily have these for the target domain, right? We don't have these consumer images. So we can't build triplets of this form, right? Where there's consumer images from the target, because we just don't have these. We do have these though, right? So what are we gonna do? So what we're gonna do instead is we're going to adapt a model that was trained using these types of triplets, right? Between the source, from source data. And we're going to use triplets of this form. So we're going to take consumer images from the source data, so these, and we're going to try to create these types of triplets, right, between these two domains. So the thing is, okay, do we have, we don't necessarily have shared items, right? So how are we actually going to create these, how are we going to get these labels? How are we going to associate consumer images from our source data set to images from shop images from our target data set? So what we propose to do is to propagate product IDs, or these are, like, you can consider them to be product classes, right, or product labels across these data sets. So we're going to take a two-step clustering procedure. So we're going to associate source and target images within a shop metadomain using clustering. Then we're going to propagate the product IDs from the source shop instances, or let's say IDs, to the target IDs based on the occurrences within clusters. And then we're going to use that to generate these triplets. So which assumes a presence of kind of sufficiently similar looking products across these two data sets, the source and the target. So let's look at this kind of pictorially. So we have, once again, our source data sets. And here, so let's look at one specific product ID, right? So one specific shopping item, for example. And so in the source data set, we have training data of the form where we have a shop image and we have some consumer image, which is the same, right? So we have this type of data. Then we have these shop images. We don't have consumer images, right? But we have these shop images in the target. And some of them are going to be, let's say, closer looking, and some of them are going to be less so, right? So what we're going to say is we're going to try to associate these two with each other. And we're going to say that if these two are sort of sufficiently similar, then we can consider that this consumer image can be propagated, the relevance can be propagated to the target, right? So looking at it here in the embedding space that we want to learn, let's say we represent this image with this embedding here, and we represent this image in the target with this embedding here. So what we hope is that if they're going to be in the same cluster, right? So once they're in the same cluster, what we can do is transfer the relevance of this consumer image into here. And then we can use triplets of this form to do our training and to do our adaptation, right? Because basically what it's doing, thinking again, is that we're going to say that we're going to adapt our model. We're going to adapt our embedding function phi so that, for example, these two images are close in that embedding space as well, right? Because we're assuming that given that these two are sufficiently similar, we would like to retrieve images that are sort of similar as well. So that's it for the approach. So now I'm going to go through some of the experimental results. So we experiment on two fashion data sets. So there's one called Deep Fashion, which we are going to use as our source data set of shop and consumer images. So this is a fairly large scale data set of about 800,000 images. And for each fashion item, we're going to assume that the category and the product IDs are known. So by the way, we train models, or we train, for example, embedding functions, which is the same thing in this case, on a per category basis. So by per category, we mean like we have a model for trousers, we have a model for outerwear, we have a model for footwear, etc. Right? So this is because this is a relatively reasonable assumption that you tend to at least know this information. You may not have more fine-grained information about specific items, but you at least know what category it belongs to, or it's something you can relatively easily collect using, for example, an off-the-shelf categorizer. We also have as a target data set, a data set called Street to Shop. And as you know, in alignment with our scenario, at train time, we assume that we have access only to the shop images, right? Here again, though, we do have the category labels. And this is also like a fairly large scale data set as well, with more than 400,000 images. So for some important implementation details. So as we mentioned, we're going to do an adaptation scenario where we have start off with a model that has already been trained on some source data set, right? So this model we call Deep Fashion Baseline, DFBL. So this was trained on Deep Fashion, our source data set, using these types of triplets, right? The triplets that I mentioned before. Actually, that's fine. So for example, we have these cross-domain triplets, right? So these are cross between consumer and shop. And then we have these intra-domain triplets as well. And we found that all three of them are important to include. So all of the proposed models are going to rely on this baseline model, right? So they're either going to be using this model as a feature extractor, or we're going to be fine-tuning the same model using pseudo labels that we achieve via clustering. So we cluster using an algorithm, a recently introduced one called Finch algorithm, which is a hierarchical clustering algorithm, which perform well in this scenario. And you can imagine that clusters can have different distributions of source and target data. So we retained only the clusters that contain images from both the source and the target, right? Because we're not interested in clusters that only have images either from the source or from the target. So just to show you some examples of some of the pseudo labels that we collect. So here we have, so once again, thinking back to the clustering problem, right? So we're clustering within the shop meta domain, right? So which means that we're clustering images from Deep Fashion shop to Street to shop altogether, right? And what we're showing here is some images that have landed, or some items that have landed in the same cluster, right? So for example, this one and this one landed in the same cluster, which means that they're both become associated with this, for example, this consumer image, right? So this is why having these co-occur within a cluster implies that this relevance relationship between this image in the shop, in the source shop, and this image in the consumer source data set also is relevant to this one in the target, okay? And then here we have another example for the category of tops. And what we found was that there is a bit of noise, but we will see as time goes on, at least empirically, that this was sufficiently, these labels were sufficiently, had sufficient signal to indeed perform adaptation. So in terms of different pseudo labeling strategies, right? So I mentioned that we're going to do this, we're going to do a transfer of labels from source to target, but there are actually quite a few different ways to do that, right? So what we tried different strategies that combine the following choices. So number one is matching target items to source items. So for example, saying we're going to, given an element, an item from, or a label, let's say like a product ID from the target, we could transfer that to the source, or we can actually do it the other way around, right? So that's one choice we can make, one binary choice. We can either have separate image representations for a specific product ID. So just to be clear here, so one product can be associated with several images, right? Very often, for example, in shopping scenarios and online catalogs, you have multiple views of the same item. So you can choose to represent that item via one aggregate representation or via like a set of them, right? So this is one other choice you can do. And then lastly, thinking about our clustering situation, when you're clustering, an actual cluster may have multiple product IDs, right? So what we would want to decide is, do we discard all the product IDs that are not kind of dominant, meaning that they're not, they're not basically, there's not one kind of like most common product, or do you want to kind of propagate across all of the potential products that you might have? So this is another choice, right? Do we kind of just stick to the most quote unquote dominant product ID within a cluster, or do we use multiple ones? So we experimented with all of these. So these three binary choices gave us 8 options, right? If you just look at the combinations of all of them. And so we experimented with all of them, and we found that the most performance strategy was where we are mapping source items to target items, where we represent a product as the average of all related items, and where we're using only the most dominant product ID. And this, I mean, the intuition I have for this is that these are all kind of the options that likely reduce noise in the labeling. For example, having like an aggregate representation, or using a dominant product ID, right? And because we're doing pseudo labeling, the more we can reduce noise, the better, right? So this is my personal take on it. So now for some quantitative numbers. So what I'm showing you here are, so first we're reporting mean average precision, average across different categories. And we're also reporting top 1 accuracy, right? So what this means is that top 1 implies that the first item that was retrieved was identical. Top 5 means that that an identical item was retrieved in the top 5, and so forth. Okay, and so we're looking at these 6 categories. We're looking at 6 categories. So that's like, you know, pants, outwear, etc. Right? There's a set of them. And we're making several comparisons here. So let me just go through them. So first is our baseline. So as I mentioned, this is the model that was trained on deep fashion. And these results are all for street to shop, right? So in the first case, this is what happens if you take a model that was trained on deep fashion, you don't do anything to it, and you just simply apply it to street to shop images. Then we have our meta-domain adaptation approach, where we simply we fine-tune our embedding, but we don't fine-tune the entire stack, the entire architecture. We simply fine-tune like the one multi-layer perception layer. Okay, and then we have this last version of our approach where we fine-tune the entire thing end to end. Okay. So, and then lastly, we have 2 versions of this. One where we use ResNet 50, which is a sort of more compact, let's say, baseline architecture that's used for many fine-tuning tasks. And then we have a larger, more performant one, which is called ResNet 101. Okay, so what you can see is that adaptation does help, right? So this pseudo labeling strategy, which one might think is pretty noisy, it actually does improve performance. And then we see that it does improve performance even more, as one would expect, if we update the entire architecture rather than sort of freezing some of the earlier layers. And then lastly, as we would also expect, using a more performant backbone does add a further improvement. So that was kind of comparison to baseline. So comparing to some of state-of-the-art methods, I won't go through like too much of them, just to say that we do perform quite well compared to supervised approaches. So because this has not been, this is like not a natural comparison, because we're comparing an unsupervised approach to supervised approaches, simply because there's nothing comparable in the literature. So this is kind of, it's nice to see that even with, no supervision, we perform quite well. And so to recap, we've reached to the end. So just like to recap that we've presented this problem of meta-domain adaptation, which is, in our view, a novel and challenging problem with also practical applications. And for this, we propose a clustering-based pseudo-labeling approach, which outperforms strong baselines. And that's it. Thank you so much for listening, and I'm happy to take any questions.
Thank you. Yeah, really interesting work. And so I guess I just wanted to confirm, because I don't know this research area very well. So there hasn't been done previous research on unsupervised domain adaptation or domain retrieval.
So there's been, sure, so let me clarify. So there's been a lot of work done on unsupervised domain adaptation. What we think is new here is unsupervised or even supervised meta-domain adaptation. So what we're proposing here is this new concept of a meta-domain and to trying to bridge a gap between two meta-domains, basically. And we're not aware of this problem at all. And in particular, we could have looked at supervised approaches to this, but we were particularly motivated by the unsupervised case, which is why we really tackled that one.
I see. Okay, so let's have the audience. So if the students can either unmute yourself and speak up, or write your question in the chat window, and I'll try to read the questions. So while they're doing that, I guess what I should do is try to make a connection to text, right? So it reminded me of this, this meta domain thing, shops and consumers. It's kind of like news text versus tweets or something, right? Where you may have similar topics, but you have this really formal language versus like informal, ungrammatical, sometimes even, nonsensical text. So do you think there's a parallel there? Do you think something like this could apply to text?
Yeah, absolutely. I think, we really focus on a specific application domain, but this is really general, right? Like there's so many cases where you need to apply predictions across some sort of gap, right? So what's interesting here is that this isn't a retrieval scenario. So you might think of one specific analogy I can see being really good for text is something like maybe question answering, which I think of very often as a retrieval problem, where you might have some text that, whereas the question may be, maybe in like a different style, right, of being said, like as you say, maybe very formal or very informal. And even with these two different kinds of styles, like stylistic, like kind of text, you'd want to be able to retrieve really well. Or you might want to retrieve, like to make a really even, like maybe even a closer analogy. Let's imagine you have a very informal question and you want to retrieve from a very formal sort of like data knowledge base or something, like the kind of answer to your question. So yeah, I think there are like a lot of analogies to different text problems, text-based problems.
Right. That reminds me, in QA, I don't think I've seen any QA data sets that consider two different domains from where these passages come from. They're usually like, this is all from Wikipedia, or this is all from, New York Times or something. So that hasn't even been considered. And QA is hard enough as it is. So maybe like the next, it'll take a while until we get to that cross-domain QA type of research, but it's good good motivation. Definitely.
Yeah, no, I think it's I don't want to make artificial problems, right? I imagine that this would come up in practice. I imagine it would be relevant in practice. I think of it as being like, I think maybe because there aren't question answering a lot of them in the wild yet, maybe this hasn't come up. But I think that as soon as people start to really deploy QA systems, in a real world scenario, I suspect this sorts of things will start to become super like obvious, right? That it needs to get tackled. And not just that, we'll actually have some data, right? Because now we'll actually have people asking questions. And what we would what I would think would be cool is if we could have folks speak or text, or express themselves like via text in a way that's natural without trying to kind of conform to the system. Because in the same way that we use search engines, and we kind of know that there's a way you have to write it to get the answer you want, and what you would love is to be able to just ask the question and get the answer. This for me is like a classic example, right, of us trying to think in terms of the machine and cross the gap ourselves. And if we could have a model that didn't require you because the model itself was domain invariant, that would be like an exact scenario, I think.
Yeah, that is great. That's great. Okay, there's a chat question. Thanks for your talk. Could you explain more about evaluation? For example, I'm not sure about how we can compare two clothes are similar or not, and how well evaluation is conducted.
Right. Yeah, no, that's a great question. So for the numbers I showed you, these were evaluated on street to shop, right? And so street to shop is a data set that's been constructed, and it does have consumer images, right? So for the purposes of testing the system, we trained without access to those consumer images, but we do have them within that data set. So what we did is at testing time, for example, you have consumer images from street to shop. You have shop images from street to shop, right? And then at testing time, we take each of these consumer images on a per category basis. So for example, we take out all the consumer images that are, let's say, footwear. Then we look through the catalog, right? So the shop images that are only footwear for street to shop. We represent each of these images as embedding. So we apply this learned function, the function that we learned, to each of these. So we have for every consumer image in street to shop, we have a vector, right, a representation via this embedding function. And then we have a list of vectors also for the shop images, right, in street to shop. And then we simply compute the dot product between that query image, right, that consumer image, and all the database images within that category. And then we look at, for example, the top one. So we see what's the closest one in that embedding space. And if it's the same label as the consumer image, then it's 100% accuracy for that case, right? And then we do this for all of our cases, and then this gives us, like, for example, average top one accuracy. So the data that we use for this, so the reason that we would be able to say that the top one retrieved image is relevant is because we have that data, right? So for street to shop, it's a data set that's artificial, and we have it. Of course, in a production scenario, you wouldn't know, right? But in this case, we actually do have access to this data. We just withheld it for the purposes of training this model.
I'm curious if you actually look at which retrieved, I guess, items were not correct. If you do some kind of error analysis, are there some interesting patterns going on? I remember one of the examples you showed was like you had that polka dotted sweater, and then you had like that jacket that doesn't actually have the polka dots but has like these buttons. And I'm sure there are other examples like that. And if you look sort of closely in what's going on, like what is the model learning? What are some potential solutions to problems like that? Like can you change the loss function? Can you change, I don't know, something about the model?
Yeah, no, that's a good question. So I don't have off the top of my head kind of like error cases of this. I can speculate though. So in terms of speculation, for a lot of these retrieval problems, a lot of it is, like if you look at, there are kinds of different areas you can have, right? So the most typical one would be simply that, let's say you have the top 5 and you see that maybe the correct item is, I don't know, maybe it's not in the top 5, it's just a bit lower down, and you have like, things that are ranked more similarly up top. And there very often are reasons like that, right? Because fundamentally, especially with images, and I guess this applies to other modalities, it's very hard to get the model to focus on what you consider to be domain invariant, or what you consider to be what you actually want to look for, right? So if you do very naive similarity metrics between images that aren't trained well, then, for example, you might have an image that they're in the same environment. Let's imagine one has a white background, the other one has a white background, a super simplistic example, right? Then they might be totally different items, but because they have a similar context, then you might consider, oh yeah, these two images are similar, they're relevant simply because of the context, not because of the item, right? So that's like a very simplistic example, but some more similar examples might be, for example, like if you have this, this jacket that has buttons and the other jacket has buttons, even though as far as we're concerned, they're not relevant because we don't care about the fact that they both have buttons. We care about the fact that both of them are, for example, like, has polka dot pattern or something. It's hard for us to kind of like create a loss function and create like the types of examples to have the model make that distinction we want to make. So it's kind of like an alignment problem, right? In the sense that it's not going to be possible for the model to, in every single case, make the semantic connection that we are hoping for ourselves. So I don't think it's I think there's a fundamental limit there, and beyond kind of having more data or maybe coming up with a very clever loss function, it's hard to think about. Then yes, that's like a tricky one. That's kind of like the crux of why this is difficult, I think.
Yeah, of course. Okay, so we have a hand raised. Kwansute, you want to go ahead?
Okay, thanks for the great talk. I'm just a bit confused about what's the result of this learning. So after learning phi function over the meta domain, so is it used to generate the pseudo label of a consumer image from the target domain?
Sure. Thanks for that question. Let me try to hopefully clarify. So the pseudo labeling, you can consider it. So yeah, let me just go through kind of step by step practically, right? So we have our baseline model, right? So deep fashion BL, right? That was trained on the deep fashion source data set. Maybe I can even go back. Let me see. Let's show. Yeah, maybe here. So let's say we have this source data set. In our case, it's deep fashion. So we train an embedding function, right? So this is what the model that we have at the get-go. And what we like to do is adapt the model, right? So let's say that our source data set, we use it to train like an embedding function that we call phi, let's say kind of prime, okay? And what we like to do is to adapt phi prime to our final embedding, right? Which is just phi, okay? And we're going to make this adaptation by fine-tuning using the pseudo labels that we create, okay? So what we do is this. So we take representations of shop images using phi prime from the source and the target. We put them all together and we cluster them, right? And we get these clusters. And then now that we have these clusters, we're going to make these associations between images within a cluster. So for example, in this case, we're going to say that this shop image from deep fashion is in this cluster, and this shop image from street to shop is in this cluster. So we're going to apply the pseudo labeling structure I mentioned, where there are many options. And let's say we say, okay, this label we're going to consider it to be relevant to this one, this image, I should say. And therefore, we're going to assume that this query image should be close in the embedding space to this shop image, okay? Yeah. And so once we have that, we have this triplet, right, of query image from source, positive image from target, and negative image from target. I didn't discuss much the negative image, but this would be an image from the target that's not in the same cluster, right? So we're going to assume it's like it's not relevant. And we're going to take these types of triplets that we've just constructed, and we're going to use it to adapt, to fine tune this model, right? And then we're going to have our final embedding function. And this is the embedding function we're going to use at test time.
Okay, so we don't have a consumer image from the target domain. So instead we use the consumer image from the source domain, right?
Exactly, yeah.
Okay, thank you.
Thank you.
Yeah, so what you just talked about just now about negative images. So is there something you do with the negative? I mean, you could imagine doing something kind of like contrastive learning where or you can have negative images that are very different, or negative images that are close to your positive images, and so on. So has that been done, or are you thinking?
Yeah. Like the funny thing is when when contrastive learning became very popular recently for self-supervised tasks, in my mind, I was like, well, this is what we do all the time, right? With learning to rank, we do like literally this. So because yes, I didn't discuss the negative images very much, but they're very crucial for the reasons that I think you're hinting at, right? As you say, we can have negative images that are very far. We can have negative images that are very like close, right? And by far and close, I mean, going back to our learning to rank equation, we can have negative images that are so far from the query that they basically, they don't really return a loss signal. And so they're not informative, right? Like, for example, if you have negative images that are very different, then very often this loss will just be kind of zero very often. And then you just won't even have like any loss to try to reduce to backpropagate on. So actually finding examples that are difficult, like what it's crucial to make this work, to actually learn something. And so there's this whole space of hard triplet mining, where there are many papers and many works that are just all about, here's a new way to mine hard triplets, right? So triplets where this distance is not too small, not too big, right? So yeah, so in our specific case, what we've done is we've taken an approach where we call it like a batch hard approach. I think this is a term, I don't think it's a term we made up, but so it's a term where basically at every kind of, we construct a batch, right? For a specific, as we're going on training, we construct a sequence of batches. And for every batch, what we do is we do a forward pass, right? With a set of like our potential triplets, right? So let's say we have a batch of images that we've sampled. Within that batch, we can construct quite a few different triplets, and we do a forward pass. We find the triplets that have like actual loss, and then we only backpropagate with those, because then otherwise, if we were backpropagating with everything possible, most of the things we would be backpropagating on a zero loss, so it'd be kind of useless. So basically, we just try to find the hard examples and only backpropagate on those. So that's like one approach to it, but there's a whole space of research on this.
Yeah. Okay, there's a question in the chat. I'll read it to you. And this is from Goyan An. Thanks for your great talk. Do you think the current fashion search techniques already offer good user satisfaction based on your experience in Facebook? What is the most difficult thing to develop most difficult thing to develop a better fashion search engine?
So yeah, that's a great question. Unfortunately, I can't answer it, as this is not actually what is used currently in Facebook, and I can't talk too much about that. I'm actually not even on that team. What I would say is are things that tend to be difficult about this problem is there's a lot of practical complexities with respect to having models that are like trying to draw the line between what granularity of models you want to create. So by that, I mean, it's very hard to get a model that is, let's say, that works across different categories, right? So it's very hard to get a model that works for both trousers and footwear and outerwear. So normally you would try to segment, right? Segment your space. But you can think of it, rather than being just one kind of cluster, like one segmentation level, you can think of a hierarchy of different levels, right? So you can think of this whole space of consumer images, even if you just focus on quote unquote fashion, right? Or like apparel. There's a huge hierarchy, like you can think from coarse grain levels to very fine grain levels that where you can decide, and deciding where to do that, and it's tricky for different reasons. As you go down the hierarchy and it gets more fine grained, you start to have like fewer data samples per kind of like let's say node within that tree, right? It also becomes more computationally complex in some ways, because you just have more models that you have to deal with. You have to choose the right model. So deciding this trade-off between accuracy computational efficiency. It's very tricky. Also because let's think, right? If you have a model, if you can think of a tree from apparel to outerwear and footwear to certain styles, right? Like in terms of footwear, sneakers versus, I don't know, stilettos, right? And as you keep going down, if you would like to have a model for each of these, train a model for each of these, that means you need to store for each of these, and then you need to have a representation for each of these. And this representation is specific to that, right? So if you can think of, if you go down one specific branch of the tree, you can have, for every node in that branch, you can have a different representation of that item, right? So you can have one shoe, and you can have it at a top layer representation, which is like an apparel. You can have it at footwear, you can have it at like a stiletto, etc. Right? So that means that you're starting to multiply your representations. And so then there's an explosion in terms of storage you need, right? To actually store the stuff. And when you're thinking of like hundreds of billions of items, that becomes like very tricky. Not just in terms of storage, but also in terms of latency when you're actually deploying the different models, right? The time it takes you to figure out the right representation you want to actually perform the search, right? So to make the computation between your database and your image, your query image. Yeah, so and that's just kind of like one piece of it, but these are some of the things that start to be really relevant when you're trying to do these applications at scale.
Okay, I have one last question, which is about the future application domain. So can you, and my general question is, how far apart or how close can these meta domains, or can these domains be? So we're looking at consumer versus shop images, but can you look into, for example, like the healthcare domain where you're looking at MRI or other types of medical images, and can you say like X-rays versus MRI, or is that like not possible at all, or or different machines, or how does that work?
Yeah, no, that's a great question, right? So in the specific case we looked at, I would say that domains were relatively close. I think, yeah, if we're thinking, for example, of medical images, like what's needed, right? Let me try to find like a good, yeah. So if we're looking here, right, what we need is we need to be able to assume that this gap is representable by this gap, right? As you can kind of approximate it. So if we can think of like, yeah, so X-ray images versus like some kind of, I don't remember the name of another one, but let's say, I don't know, ultrasound. It's not really a great example, but anyway, then the gap might be too big, right? Because the gap between these two in that case may not be the same. It may not be generalizable to a meta domain gap. So because, for example, in the case we've mentioned, right, like the gap we're looking at is really like a sensor domain gap between these two. So yeah, actually, now that I think about it, yeah, maybe in this case, in the specific case you're thinking of, this gap between sensor modalities in the medical imaging space, yeah, now that I think about it, I'm a little bit less skeptical. Yeah. Yeah, I don't think that's necessarily a problem. Like, I think what's difficult is what I think would be needed, now that I think about it a bit more, is if we can think of a separate target data set where this domain gap is similar to this domain gap, then I would expect it to work. So let's say in the medical domain, you had like you already had a source data set that contains images from both modalities. So for example, from MRI versus something else. If you can already have these two domains represented, and then you had like some new data sets with new MRI images, then I think you'd be able to use the same approach.
Yeah, that'd be really great to try for you or anyone else. Probably not me. All right, so we have a hand raised by my co-host Minhyuk. Go ahead.
Actually, there's also another question in the chat. I guess you can go first with it.
Oh, right. So the chat, thank you for your talk. As I understand, we're trying to learn phi function that sends images to domain-invariant space using pseudo labels found by clustering method. What I am confused here is that it seems like we're conducting pseudo labeling in domain-invariant space with not trained phi and use it as pseudo label. Is that correct?
Yeah, that's it. Yeah, no, I completely understand. And that's actually like just a not refine this schematic because it does look that way. You're right. So it does look that way that we're clustering in this space, right? So what I should have done is remove this and just say basically, and put, for example, phi star here, okay? Because this is kind of like, and then say, we're going to cluster in this space, and then we're going to use these triplets to train a new space that's meta domain invariant. So the space in which the space in which the clustering is happening is not the same space in which the learning is happening. So that's a great question. I hope that clarifies it.
Okay. And so Minhyuk, you can go.
Yeah, thanks. And thank you for the great talk. It was really interesting and inspiring talk for me because actually this is a kind of real problem in the 3D vision domain. So basically I'm working on the 3D vision domain, and here basically many people are basically working on like retrieving some 3D models to match some sort of the 3D noise scans. So this is kind of real problem in this domain. And also this is the problem that it's very, very difficult to get some kind of annotations. Basically for the 3D scans, it's really hard to see what's the kind of the right 3D models that can really match the 3D scans. And also basically if you train the models for the scenes that you scanned at KAIST, and then somehow you try to test the models in the OP scenes at Facebook, for example, there will be lots of things that you do some sort of the adaptation. So it's kind of very interesting and the inspired talk for me. And one big question for me was that basically, so my understanding is that the neural net model, which is trained with the contrast of the loss, is the case that basically you are assuming some sort of the one-to-one correspondences. Basically, I guess this is the case that you are assuming that you have the one corresponding, basically like there's some sort of the one-to-one mapping between the shop images and the consumer images. So that's the way that you can define some sort of the positive samples and the negative samples. But I think you also have shown some examples that like there might be some sort of the one-to-n correspondences. Like for some of these slides, I think you have shown the shop image that has a model wearing like two clothes, which means that one shop image actually can have some like two clothes images, basically, which means they can be mapped to the two different kinds of consumer images. And I guess there might be also other way around. Right? For the one consumer image, like that image somehow has like two clothes, or somehow it captures like a kind of the item somehow partially, so that there can be some multiple shop images that can be somehow described by the one consumer image. Then in this kind of the case, I guess the idea of like just using the contrast loss may not just work. So somehow I guess there might be some sort of the new neural model that can somehow handle this kind of the one-to-n correspondence cases. Would it be the case, or yeah?
Yeah. Well, thanks for that. That's a great question, and I do agree. There are lots of parallels to. This is a very, I think, generic problem across retrieval cases, and so yeah, I can definitely see your kind of 2D to 3D retrieval thing being super relevant, especially with the adaptation to different scenes and things like that. In terms of the question about this one-to-n mapping, so I didn't go into a ton of detail on this in the talk, but this is indeed like it's an important element, right? So once again, if we're thinking about clustering, so if you look here, you see that, for example, we're clustering across domains, across data sets, right? So we're clustering within a meta domain, in this case, a shop domain. And indeed, right, it's possible that, for example, this item is represented by multiple images. And it's the same. It's possible that this item is represented by multiple images. So we had different choices to do here, and there's like quite a bit of a combinatorial explosion about the different choices you can make for this. So one thing that we found to work well, what we found to work best was to represent a product with the aggregate. In our case, I think it was simple the average of all the associated images, right? All the images associated with that item, okay? And I think in this case, we would have done something similar. I'm not sure we assumed that we had access to that type of information about like which item each belonged to. We might have, but in any case, we could have treated each of these as like one. We could treat each of this as kind of like one instance and then map it to the average representation of this one, right? So we can do that. And then for the negative images, what we did, which I don't think I've specified, is that the negative image would be in a different cluster. And there is the assumption that that any image that shows up in this cluster is not going to be considered a negative example, right? And a negative example should be from some cluster space it should be within a different cluster, and it should be kind of like sufficiently close that it's a difficult example. So in that case, we resolve the one-to-n problem that way by kind of collapsing it into a one-to-one problem, at least where we assume that we are going to represent shop images by one item. I don't know if that answers your question.
Yeah, I was just thinking some cases like somehow, so these are all the cases like every kind of the items, either the shot images and the consumer images are kind of the map to the points in the embedding space. But I thought that there would be some possible ways, like some kind of these kind of images can be mapped to some kind of the regions or some distributions over the embedding space, so that you can actually have some sort of the inclusion relationships with some other kind of images. Would it be doable in this kind of the model?
You say a causal relationship?
Well, no, some sort of inclusion relationship, like one, like if you have the one-to-n, it's kind of the inclusion kind of thing.
Right. Yeah, I could see that. Yeah, so I can, yes, I see what you mean. That would depend, right? So let's say that we had, for example, these shop images here, and we had multiple ones associated with this ID, right? So let's say we have this item and it has like multiple images. Then we could do some inclusion thing where we say that maybe the other images are not in the same cluster for some reason. Maybe they're in a close by cluster. But because this image is in the same cluster as this one, we can kind of include all the rest of them as well. So we can kind of make this kind of like transversal labeling. What we found though with those types of something similar is that it tends to introduce a bit of noise. So because, for example, what we found was important is that when we did the clustering, that we focus on clusters that have a high quote unquote purity, basically. So if, for example, you had an item where the images are kind of spread across different clusters, then that's not like a great example to pick because it's a bit ambiguous, like where it belongs to. And so therefore, the kind of relationships that you would mine that way, these pseudo labels would be a bit ambiguous as well. So we would focus only on extracting triplets with examples from clusters where there is like high membership to a specific cluster, right? So this is what we meant by the term dominant. I didn't really describe what it meant to be dominant, but what it meant to have a dominant item in a cluster, it means that, let's say you have X number of images of a certain product, and then like the dominant cluster is a cluster where kind of the number of images of that item within that cluster is highest compared to all the other clusters, right? So that just means that basically the clustering is compacting. You don't have them kind of spread all over the place. And so that we found was very important. Well, you can see so I didn't really describe what each of these meant. But right, so we have a lot of different labeling strategies, like different ways to make these different choices. And we found that this one worked best because like I said, so my intuition was that it reduced a bit of noise. So I think trying to have these a bit more complex inclusion relationships, it makes sense. But because this is a relatively noisy scenario, my suspicion is that it introduces more noise than signal.
I see. Yeah, actually, my second question was actually about like, what if we somehow do this kind of the same thing without kind of the pseudo labeling for somehow? So this was basically the case that somehow you are basically classifying all the shot images in the target domain as kind of either like the positive or the negative samples by basically checking the distance to the shot images in the source data sets. But I was kind of just imagining some kind of the situation somehow you embed everything without doing this kind of like binary classification, but somehow embedding everything based on just kind of way to maintain the distance between the shot images in the source data set and the shot images in the target domain, the data set. But I guess you already kind of answered the question somehow. There might be some issues with the noise in this case, right?
Yeah, so that's like, there's like some very interesting work done by like this was in 2011 or something, I think, by folks actually both of whom are now in FAIR. So that's like Kristen Grumman and
I see.
At least Kristen Grumman, yes, and her students were involved in this work on what they call relative attributes. So this reminds me of what you're suggesting, in the sense that even though this is not continuous, a continuous distance, because yeah, there's a full spectrum, right, between like a binary relevance and non-relevance, and like just a continuous one, for example, based on distance. And this work was doing something that I think was more kind of just hierarchical, or kind of just segmented, saying like, you know, relevant, maybe relevant, or not relevant, or something like that. So you can think of having it increasingly fine-grained to the point where it's continuous. But yeah, that is like very interesting. And I think if you have relatively clean data, then you can do that sort of thing. In our case, I think it would be a bit noisy. So you want to err on the side of just like putting a binary threshold that's relatively high and relatively conservative. But I definitely agree that in some supervised scenarios that could make sense. Another place where you've seen things that are like this, where you focus on like a kind of like a distance curve as opposed to like a binary thing, is in some like a different problem space called semantic retrieval, which was done by some of my colleagues in Xerox back in the day. And so this was specifically in this scenario where you wanted to retrieve based on a notion of just holistic semantics. So for example, let's say you had an image of that is hard to capture in one thing, right? So, and it's hard to say what's relevant or not. So let's imagine you had an image of like a scene of, let's say 2 kids playing in a park, right? And then you had another scene that had like a kid playing with an adult in a park. And then you had another scene of like an adult playing with another adult in the park. It was like, what does relevance mean in this case, right? So of course you can just sort of ask people, is this relevant, is this not? But it makes more sense to have kind of like a spectrum, right? Like to have like different degrees of relevance. And in that case, some of the things you mentioned make sense. So yeah, no, I think it's a very interesting problem. And it has been like looked at in some other scenarios, and I think it would make sense here as well. Yeah.
Yeah. Thank you for the great answers. By the way, also Christine gave a talk in this colloquium last time. Why we didn't discuss this topic?
Oh, well, she has so many things to discuss. Thanks so much for the questions. Yeah.
Okay, so I think we are done. I mean, let me give 30 seconds to our students to ask their last burning questions. Otherwise, I think we can close this session today. So again, thank you very much, Naila, for joining us today and for giving this great talk. And it has inspired me to look into, this cross-domain retrieval, which I really think is going to be relevant in the QA domains. We've done some QA recently. So, all right. Okay, no more questions. So thanks again, and see you soon.
Yeah, thank you so much once again. It was a pleasure.
All right,
Thank you very much.
Bye.